Well, good morning, Cisco Cohort 1. It's Mark, and I'm going to be going today through the Chapter 4 material, which is talking mainly about IP addressing, this IP addressing scheme. And then Wednesday, we have two labs. Lab 2125 is on the MAC addresses. We talked about the data link layer and the MAC addresses last week. And then this week, we're going to talk more about the layer 3 addresses, the logical IP addresses. And there's a new version of Packet Tracer that's just been released about a week ago, and it's got some really great new features. One of which, since a lot of you guys, even you guys that come and report in person and take the labs, I can't allow you to get your grubby grimies on the wires and plug the things together yourself. You have to kind of stay stuck on your workstation and work on it there. So the new version of Packet Tracer has got some great physical layer features that you can do your rack and stack. You can bring in routers and switches and put them in a rack. You can bring in desktops and laptop machines and put them on a table. You can plug the wires together and see the wires connecting one device to another device. So I'm going to give a demonstration of that after I talk about the death by PowerPoint stuff with regard to this Chapter 2 and Chapter 3 labs that we have assigned for Wednesday. Okay, so let's see now. I need to go and start the PowerPoint presentation. And the first slide looks like it's popping up good. Okay, so Chapter 4 topic is network addressing. And before I pop to the next slide, I talked last time a little bit about data link layer addresses. We had that dreaded, feared, and hated OSI 7-layer reference model, and then we had the more simplified TCP/IP model. Hang loose, someone's joining. I'm going to track their attendance. And I give this a comparison that, that MAC address, the Ethernet address that's burned into every Ethernet adapter, doesn't matter where it's one that goes inside the computer or if it's like a USB. Some of these new laptops are so skinny that they can't put the RJ45 Ethernet plug on them. You have to plug in like a USB adapter with a little pigtail on it, and then it has that big fat RJ45 connector. But all those Ethernet adapters have a sort of a burned in or hardware or physical address that they get for life, and that never changes. It's kind of like your Social Security number. You get that for life, and normally you never change that. Your cell phone has a burned in. It's kind of like an electronic serial number, NAM number that's built into every cell phone, and that number never changes. Now you can change your phone number. You can go to a different carrier and get a different phone number, but your physical phone itself doesn't change any. Nobody has to open up the phone and solder in new chips. It's all stuck with the same address. And the network layer address is like it's like the street you live in or the telephone number that your cell phone gets. And like telephone numbers, it has an area code part and then the 7-digit local number part. And network addresses are like that. The left part of the number tells us which network it's on, what company it belongs to. And the right part, or if you're a home user, what cable company or telephone company you're attached to. And the right-hand part of the number identifies your individual device that's on that particular network. Okay, so what we're going to see is IPv4, IPv6, what are all these V's? What are all these numbers? Oh my gosh. Well, when the IP addressing scheme, they first came up with this, back in the 70s, it was a 32-bit value. And they came up with 3 different sizes of networks, sizes for large companies, sizes for medium companies, sizes for small companies. And they never figured that there would be this big internet thing that took off and became popular, and we would need billions and billions of addresses. Because with 32 bits, there's only 4 billion different combinations. And you can't use every combination. Some of them are reserved. So about in the middle 90s, this started to become a big problem. We were just running out of these old style IP version 4 addresses. And so they came up with some Band-Aid patch schemes to make them last a little bit longer. And then they started sounding the trumpet and saying, we need to go to a new network addressing scheme that has more bits in it. Instead of 32 bits, they went to a scheme called 128 bits. That's what we call IP version 6. So with IP version 6, there's more than enough numbers now where every thermostat, every refrigerator, every Game Boy, every device can have its own particular unique IP address. And we're going to look at that at the end of the chapter just very briefly, kind of an overview. So mainly we're going to talk about IP4 addresses. So IPv4 address, he says it's a logical address. It's like a logical number on your telephone, not the built-in serial number, the electronic serial number, NAM. It's a logical number. It can be changed in software. It identifies your individual telephone if it's a cell phone. It identifies your individual computer if you're using a computer system at home or at work. And it has to be unique on the network. So in this case, the user is at, I can't tell whether he's supposed to be a home user or a business user. Maybe he's a business user. He's WFH, working from home. And he has that particular IP address of 192.168.200.8. And he's using a web browser on his screen, and he's gone and typed in the address cisco.com. He must be the purchasing manager for the company. He's going to cisco.com, and he's going to buy some Cisco devices for the new office they're opening across town. And so that cloud thing, whenever you see that cloud diagram, that's a sign that we don't know what's in there. It's just so far as we're concerned, magic keyboard elves are connecting us together, and we'll be able to send our information. Our packets can be delivered back and forth from wherever we are to whatever we're going to. So on the top server on the right-hand side, he's talking to the Cisco web server, and he's going to go and research what types of routers and switches and other Cisco products he needs to put in his new sales office they're building across town. And he may need to go to business A or business B to buy paper or desks or things of that nature. So he's all connected that through the internet. So he has a unique address that's present there in his small business home office or commercial industrial office where he's working at. It's associated with a network interface card. So that logical address, he's the guy in the purple shirt there has got 192.168.200.8. That's a logical address. And we're not shown it, but there's inside that computer is a network, Ethernet network adapter, and it has that 48-bit binary address, the network interface card's address, the MAC address. One of the labs we're going to determine the MAC address of our PC that we're using in the lab. In the other lab, we're going to determine what our IP address or network address is with that particular one. So there is a correlation between the two of them. There's a special protocol that matches them up together. So if I want to send an Ethernet request to my home router, I need to know what my home router's physical MAC address is. So there's a special request I send out. I'm broadcasting a message saying, calling all stations. If your IP address is 192.168.200.1, maybe that's his home router. Tell me what your physical address is, because I need to put something in a Ethernet frame and send it to you, and I have to have your physical address to send it to you to do that, so you can take action and choose the best path and relay it on to the Cisco site. So if you take these 32, these guys that came up with this IP, they were very smart. A bunch of smart guys stayed up late one night and came up with this scheme, and they knew that if they, most of the people that use computers aren't network engineers and don't think in binary. So they knew that if they represented these addresses in binary, that if you look at 32 binary bits, you go blind. It's just a bunch of numbers. It's very difficult to look at them and realize what number they are. So they came up with this scheme called dotted decimal, in which when you configure IP addresses on the device, you write decimal numbers. You're used to working with decimal numbers. That's third grade math. That's easy to do. So the binary values are changed to decimal values. So an IP address is 32 bits. It's divided into 4 chunks of 4 8-bit binary values. And each one of those 8-bit values is going to be reduced to an easy to read and easy to type dotted decimal address. So 192.168.1.5 is the decimal equivalent of this bit pattern we see here, this binary address. Now, I made this representation that a telephone number like 817-515-4455, my office telephone number. The 817 part is like the region of the country to connect you to the proper telephone company region. And then the 515 says, oh, this is the number that belongs to Tarrant County College. And then the last 4 digits, South Campus gets all the 4,000s. Northeast Campus gets all the 5,000s. Tarrant County bought the 515 prefix, so Tarrant County College owns the 515 prefix. So we divvy it up among our campuses with different banks of 1,000. So IP addresses, 32-bit IP addresses, are similar. They're hierarchical, which means the left part is the bigger part and the right part denotes the individual part of it. So the network number in telephone numbers, it's easy to tell because in America, the first 3 numbers is always the area code. The last 7 numbers always represents the individual telephone in Fort Worth. 817 is Fort Worth. The last 7 numbers is some telephone number somewhere in Fort Worth, somewhere in Tarrant County. Now, if you go to other countries that have different numbers of telephones, it may not be a 3-digit area code. It may be a different number of digits in the area code. So networking addressing is sort of like that. Some number of the numbers to the left part in our situation is on the right-hand part here, it's the green number. On the left-hand cloud, it's the blue number. This is the network prefix or network number. It's like an area code. It tells what network it belongs to. And the right number is, well, which individual PC or server or printer or whatever network device is on there is a part of that individual network. So the network number and the host number. So logical IP addresses is that some number of bits are network bits and some other number of bits are host bits. And we have a little yardstick or ruler that we use to tell us, well, which one of these bits is a network prefix and which one of these bits are the host number, the individual number on that particular network. It's something called the subnet mask. I don't like that term, subnet mask. Sounds like Phantom of the Opera. He's trying to hide something from us. I would rather it be called the network yardstick or the network ruler. It's telling us which part of this left-hand part of this IP address represents the network, the whole company's number, and how many bits are left over on the right that we can assign to individual devices. So in this particular example, try to get overwhelming with binary here, but in this right-hand diagram, the first 3 numbers, the 192, let me turn on my pencil. So this part here is the network prefix, like an area code. This is number 99 device on this particular network. Now in binary, that's 8 bits, and this is no harder than 3rd or 4th grade math. Don't think we're going to do calculus or something here. If I had 8 bits in binary, that's 2 to the power 8 possible combinations. So there's 256 possible combinations of numbers that I could have on this particular network. Now, if I have more than 256 devices, I would have to have a bigger network. But this is a very common size of networks in networking. It's just 3 numbers are the network number, and the last number on the right is the host number. So when you pick up the telephone and you want to call somebody for free, it's probably going to be 817, some number in Fort Worth that's a free call for you. If you want to call somebody long distance, well, the rule used to be you have to dial 1 and then the area code and then the number. With cell phones, I've noticed you don't have to dial 1 first. And I think if you've got one of the newer style telephone numbers where they took away your copper cable and they maybe give you, I've got the phone company service. Where my internet connection data and my telephone come in on the same wires. And I don't have to dial 1 before the number, but that was the old rule. And remember, maybe you guys don't remember, we used to only have 1 area code in Fort Worth. It was 817. We used to have only 1 area code in Dallas. It was 214. But then in the 90s, we had this proliferation, this explosion of dial-up modems before we had broadband, and fax machines, and things of that nature that were taking up all these. There weren't enough 817s. It's only about 10 million numbers. And so now we have 5 or 6 area codes for Dallas and 5 or 6 area codes for Fort Worth because the networks got too big. So if they'd gotten even bigger than that, we'd have to have more than 10 numbers in our telephone number system. So when a device on a network wants to send something to another device on the network, he has to figure out, it's the same decision you make when you pick up the telephone. Let me give you another example. When we're at school, I can pick up the phone, I can dial a 5-digit extension and dial someone else at Tarrant County College within the Tarrant County College PBX telephone system. If I want to dial off campus and like dial the weather or something like that, I have to dial the number 9 to get an outside line. And then I get an outside dial tone, and I can dial the 10 digits of that outside number. So I had to make this decision. Am I calling someone else that's within the college? I just dial their 5-digit extension. If I'm calling someone outside, I have to dial 9 first, get the outside line, and dial their number. So when host computers on the network, I use the term host. That just means a device that plugs into the network and takes up an IP address, like a desktop PC. H1 in our diagram. When a host machine H1 decides he wants to send something to another device, he's going to compare his address with the address of the destination machine he's trying to talk to and try to figure out are they on the same network. Now, if they are on the same network, he can talk to them directly. In my PBX analogy, if I was calling, say I'm in the classroom and the projector bulb burns out, and I have to call the lab manager and say, come change the bulb. I just dial a 5-digit extension, and I could get in touch with the lab manager next door. If I had to order a new bulb myself from the vendor, I'll have to dial 9, then dial the number for our projector bulb supply company and order it from them. So computer H1 is trying to talk to H2, and the first 3 numbers, the 192.168.1, are both on them. That's the network portion. That's like the area code. The last number is 44, and I'm trying to talk to 66. So I figured out I don't have to dial 9 for an outside line. I can just talk to him directly. I don't need any help. I don't need the operator to do this for me. So the thing that tells us this is something called the subnet mask. And the most commonly used one is, pencil still on? Yeah, it's this one. Because with the subnet mask, 255.255.255.0, that tells us that the network prefix is the first 3 quarters. Commonly 192.168. something. The number of bits that are left over, there's 8 binary bits left over. How many host machines do we get that we can assign to real physical devices? Well, it's 8 bits. 2 to the power 8 is 256. We lose 2 of these numbers because the all ones value is reserved for this broadcast function, and the all zeros value is reserved for the network identity itself. So we get 254 that we can use. So some different types of IP addresses. In the classical networking ended in 1995. However, we still use it in education as an example of how to use a subnet mask. Now you notice that in these top part of the diagram, they have some slash numbers. So instead of having to write out 192.168.100.1 space 255.255.255.0, they use the slash numbers to indicate how many binary ones is in the subnet mask. So very commonly used addresses here, 192.168.1.1 slash 24 means there's 24 binary ones in the subnet mask. That's equivalent to 255.255.255.0. Small networks, maximum 254 hosts. So as I said earlier, these guys that designed this were very wise. All the networks that had been invented before then had a fixed number of network bits and a fixed number of host bits. Couldn't change it. You're stuck with the same size everywhere. With TCP/IP, they said, well, maybe we're going to have some big corporations that need big networks, like Class A networks. Well, it's a /8. That's 24 host bits. That's like, several million devices. Well, if you're a huge corporation, you might need that number of devices in your network. Class B networks were medium-sized businesses, 16 host bits, 16 network bits, and 16 host bits. So that was 65,000 possible addresses. So when I worked in the 90s for Harcourt Brace College Publishers, we were part of a big publishing chain, had 100 offices throughout the world. We're on every continent except Antarctica. We had about 15,000 employees. So we had a Class B address. It was 167.208, and I'll never be able to forget it because I statically configured it like 1,000 times at least. So that means we had 16 host bits left over. Well, what's 2 to the power 16? Oh, put on your binary hat and get out your Windows calculator. It's 65,536. 2 to the power 16 is 65,536 possible numbers. We only get 65,534 of them, but we only had 16,000 employees. So that was a big enough bunch for our company to use. We couldn't have used a Class C because they only had 250 odd available addresses, and we had many more than that. We had thousands of employees. So in the mid-1990s, we started running out of this way of using only 3 sizes. And they came up with a new scheme called classless addressing that gave us the ability to use custom sizes. So the problem was, before about 1995, if I was a company that had 300 employees, I would not be given a Class C. I would be given a Class B, and I would be wasting 99% of the space. That's one of the problems, is many companies were only had maybe 1,000 employees, and they got a Class B address, and they were wasting over 90% of it, and we just ran out of spaces. We ran out of available network spaces. So in classless addressing, they come up with a scheme that says you're not stuck with small, medium, or large. We have essentially 30 sizes. And one of these is going to be a better fit for your company, and you won't waste so many addresses. So in classless addressing, we're not just stuck with /8, /16, /24. We can use any of those numbers, up to 30, up to /30. So this, they program all the routers in all the ISPs and all the backbone of the internet with this new thing called classless interdomain routing to allow them to accept other sizes than just /8, /16, and /24. And that was a good stopgap that we're still using today as we're trying to get everybody in the world to switch over to this new IPv6 thing, which has so many more bits that we should never run out of them. Now, back to our PBX system. So if I wanted to call the lab instructor and say, please come in, one of the students can't log in, can you help him with his password? I would pick up my phone at my desk, and I would dial the 5-digit extension, the PBX inside extension for that. And let's say it was 54455. And he would come in and he would help you because you forgot your password. Now, at Dallas Community College, they have their own computer labs. Is it possible that they could also have a number called 54455 on their private internal PBX system? Of course they could. So we can have a duplication of inside numbers here. So private inside IP addresses are similar to this, as also done as an attempt to keep from running out of so many IP addresses. This private thing we saw on a slide earlier, the 10, the 192.68, the 172.16, these numbers are private inside addresses that you can use within your company, and all Dallas Community College probably uses the same numbers that we use at Tarrant County College. All the big companies are using these same numbers. Let's put it this way. Let me see if I can use ESP and figure out what the IP address of your home router is. So let's see. Think about your home router's IP address. I'm getting 192 and 168. I'm getting 192.168.1.1. So how is it possible for all of you guys to have the same exact network address for your home router as everybody else? Wouldn't that be a conflict? We're not supposed to have unique numbers. Well, they're on the inside of your home network, and they're changed, they're translated through a thing called NAT, network address translation, to that one unique IP address that you get from your cable company before it goes to the internet. So these private inside addresses are 3 sizes, A, B, and C. A is really big, B is middle-sized, C is kind of small. So Tarrant County College uses the A, which is a 10 dot. Next time you're in the lab, do an IP config on your desktop workstation, and you're going to be 10.144 or dot something, depending on which computer you're at in the classroom. We have 4,000 employees and 100,000 students. We got a lot of computers. We need a lot of numbers. The B class, 172.16, that's what we use with our Wi-Fi system. So if you bring in a device and you attach to our Wi-Fi network, you're going to see that your address is 172.16.7. The Class C addresses, when you only need up to about 200 devices, that's good for home users or real small businesses. They don't connect directly to the internet. They're only visible on the local network. They'll be translated into a number you get from your internet service provider before they go out to the outside world. Your home router does that automatically. Your home router does that function automatically. Now, the loopback address is a special address that we use to test to see if our computer has been correctly configured to be a part of a TCP/IP-based network. So maybe you've heard this number, 127.0.0.1 is a number you type in onto your desktop PC, and if it returns good, reply, 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 that means you're okay to connect to the internet. So unicast, broadcast, and multicast addresses. These are three types of addresses that are sent. At the top, the workstation H1 is trying to send a message to H2. This is a unicast. This is one-to-one. This is like when you pick up the phone and you're not having a party phone line. You know, it's like a private telephone number. It's not like Farmer Jones in the country that shares a party line with 10 other farmers. So you can pick up the phone, you can dial that number individually. It's like when I give the example of the principal's office. When the principal pushes his button and only goes into the classroom you're in, and your mother's there to take you to the doctor, he says, "Mrs. Jones, please send Jack Smith to the principal's office. He has a doctor's appointment." He pushes the button and it only goes to your teacher's class. That's a unicast one-to-one. When the principal leaned on the button that talked to all of the classrooms at the same time, he said, "Attention all students, rise for the Pledge of Allegiance. Attention all students, report to the gym for the pep rally. It's Friday morning." That's a broadcast message. That's something for everyone. So when it's a unicast message, it's, in this case, it's from the individual IP address and the MAC address of H1 and computer H2. Computer H1 looks like a desktop PC. Computer H2 looks like it's a server machine. Maybe it's sending something to the human resources server to see how much vacation time he's got left. A broadcast message goes to everybody within your network. So it's duplicated and sent out to everybody all at the same time. There's a special reserved address at the data link layer, at the MAC layer. It's all FFFF, which means 48 binary ones. Hexadecimal F is 4 ones. In the decimal, dotted decimal IP address, the host portion of the IP address would be all ones. And that would send it to everybody. So maybe you needed to do, maybe you wanted to send something to the server, but you didn't remember what his physical MAC address is. You'd send a request message saying, "Calling all workstations. If your IP address is 192.168.1.200, send me back your MAC address so I can send you a private personal message." Multicast is a sort of a subset of broadcast that's a kinder, gentler method. Let me compare unicast to people that put a message on a form in just lowercase letters. That's kind and gentle talking. People that post messages on forums in all capital letters, it's like rudely shouting in a room. Multicast is to a group of hosts. So multicast is typically used, if you are logged into one of these internet FM radio stations where you can listen to, your kind of music. He does, and there's thousands of other people listen to the same internet radio station. He doesn't send out 1,000 copies of that. He sends out one copy and it's multicasted to everybody. They can all listen to it. In networking, we typically use multicasting between things like routers and switches that they want to share routing and destination, path determination information back and forth with each other. And there's a reserved range of addresses for these, 224.239. Now, how do you get an IP address? So far, we have statically done this. In the labs we've done so far, you went into your virtual VMware machine and you statically assigned an address in it, or if you're using Packet Tracer, you went into the Packet Tracer IP configuration page, which looks similar to the Windows page, and you statically configure the IP address. Now, typically, in the real world, we don't statically assign anything except to, network devices like routers and switches. Some host devices like servers or printers, they need a constant address. And it's very time consuming and it is error prone to have to manually assign these addresses. And before, about 1995, we had to do this for everything. I was the guy that did it at Harcourt. I statically assigned network addresses to every device we had 6 floors, 80,000 square feet of the building downtown. And it was mostly Macintoshes because our business was laying out um, design, digital design of textbooks and things of that nature. And let me tell you something about people that use Macintoshes. They already know everything there is to know about computers. So when they move from one office to another office on a different floor and they needed a different network address, they just put something in themselves. Of course, it didn't work. So I had to maintain a little spreadsheet of all the IPv4 addresses that I could use. Remember, I told you that I configured 167.208.209. I configured all these addresses over and over again because 50% of our people seem to promote themselves and move to different offices every 6 months. So we had to keep changing these things. In the facilities management field, that's called MAX, moves, adds, and changes. We got to change your phone, we got to change your computer. Big problem, they keep moving around. So when they came up with this dynamic IP address scheme in the mid-90s called Dynamic Host Configuration Protocol, you know, computers just love to keep track of numbers. They love that. They love numbers. So now, computer, would you mind keeping a list of all these particular IP addresses and allocate them out to people when they need them? And when they go on vacation for 3 weeks or leave the company, take it back and have it available to be used again? The computer has no problem doing this stuff. So overwhelmingly now, both in home users and in business and commercial use, we use a DHCP server to do this for us. Your home router does this for you at home. In a business, it's more likely going to be done by a Microsoft Windows computer. So here we have a single user at home, and he's maybe have a virtual private network or something he's connected to his office. He's doing work from home, and he's been assigned an IP address from his inside secret virtual private networks or networks that you can encode everything so that nobody else can see it. He's been getting that address from the router ISP1 back at the company. DHCP servers normally at home use, if you're not using a virtual private network, you're probably not, you just get that from your home router. He gives that to you automatically. He knows what the connection is to the internet service provider, and he issues all of your devices at home, probably 192.168.100.1, something like that. In businesses, we have specialized DHCP servers. So in a small business, we might have a router do it, like here in a smaller home-based business network. The home router is also the DHCP server. He assigns IP addresses to all of the clients, and they're wireless here, but they could be plugged into. In a larger business, we're going to have a specialized server that does this. It's probably going to be a Linux or a Microsoft-based server computer, and one of the jobs he's doing besides file and print sharing and being the mail, email, and the web service for the company, he will be handing out IP addresses to all these particular devices. So how does this work? Oh, we're going to get a little technical here. So remember that broadcast address? If it was a MAC address, it was all Fs. If it was a broadcast address to everybody in the entire universe, it was 255.255.255.255. In binary, that's 32 ones. That's a special reserved address. We cannot assign that to PCs. Broadcast addresses cannot be assigned to devices. Network addresses cannot be assigned to devices. We lose those two. We got all the ones in the middle. So here's the way of remembering this. Dora the Explorer, D-O-R-A. So what happens is the DHCP client sends out a broadcast message. He says, calling all stations. If you are a DHCP server, please respond and get me started with getting my proper IP address that no one else also has. I don't want no duplicate addresses now. I want a good address so I can be a part of the network. The DHCP server will hear this broadcast message and he will respond with an offer back to the client. He says, I'm a DHCP server. I have a spare address or two. Would you like to use one of them? The DHCP client responds with yet another broadcast that says, yes, I request to use yours. Now, sometimes in corporate environments, there's more than one DHCP server. If any of you guys do this Microsoft Network Administration, Microsoft Server Admin stuff, Microsoft recommends that you have 2 DHCP servers on your network because you know what Microsoft computers do? They crash all the time. Well, if the DHCP server crashes, now nobody can use the network. So they always recommend you have two servers, one back and the other one up. So the workstation has sent out a second broadcast saying, yes, please, I will take your offer. And so the DHCP server sends back an acknowledgement to the workstation saying, okay, please use this number, 192.168.100.101, whatever particular number he gives them. And now the client machine can start using that. Now, when does the client do this? Well, when you turn him on or when you reboot him, he does this. How long does the client machine get to keep that IP address that he was given by the DHCP server? It can be configured typically at least a day, and typically more like 2 weeks. Now, what happens if you had a laptop computer and you were in the South Campus Business Building and you were attached to our Wi-Fi, and then you took that laptop computer and you went to the library, which has a different network? You would lose the IP address that your laptop had when it was in the South Campus Business Building, and you would be reissued a new address that's proper for whatever network was in the library when you walk into the library. So this is a kind of a roaming feature with Wi-Fi clients and walk around and they automatically stay connected to the network. So Dora the Explorer. Now, let's talk about how before they were called routers, they were called gateways. As a matter of fact, when you go into the Windows configuration screen, it has the first line says, what's the IP address when you do a static? The second line, what's the subnet mask? The third line is, what's your default gateway? So they used to be called gateways. Now they're called routers. Sometimes they call it the default gateway router. I like to call it the friendly neighborhood router. So here you are at home on your desktop PC. And here is the home router that you connected to your cable company or your telephone company connection to the internet. That's the one device that, now routers separate networks. Routers connect networks together. In this diagram, we have two networks. We have the home network of the home network devices, and then we have the network that goes through the cable connection back to the cable company internet, or to the telephone line connection back to the phone company internet connection. So the router is going to separate these networks out, and they're going to have different network addresses in the sense that Fort Worth is 817 and Dallas is 214. So this default gateway port that your PC is attached to right here is your connection to everything that's in the internet. So it's very important that you know his IP address and MAC address if you want to talk to someone not at home, but in the rest of the internet. So routers are gateways to other networks, all the other networks. So who is on the inside? He says internal hosts must be assigned addresses within the same network. We can either do this statically. Well, that's crazy. No one does it statically anymore. Oh, we'll do the printer statically. We'll do the server statically. But everybody else, we're going to use DHCP because it's such a drag to follow people around and have to, when they move to the office, to set them up with an IP address. So DHCP does this automatically. It's a good little program. So this is where we're going to either statically, or DHCP is going to automatically give this workstation his unique IP address, which is a good address, the subnet mask, which tells them how big the network is, the default gateway, which tells them how to connect to the rest of the world, and other network information, such as this DNS lookup thing. We can't expect our users to type in 32-bit binary codes for Cisco. They want to type cisco.com. And DNS, which is I call the Directory Information Operator of the Internet, he will take the cisco.com and he will look at and say, oh, that's the 32-bit IP address, and he'll put it in there for you. So the network that's on the internet side is the external or outside-based networks. Usually you get this from the internet service provider. Maybe you will get this from your employer if you're a big company, if you're using like a VPN or something to dial into your company's network. So this integrated router, your home router, is an integrated router because it's a router function. It's also got a little 4-port Ethernet switch. It's also got some Wi-Fi connectivity, and it's the boundary between your local network, which you control and you choose the devices, and the external network, which whoever you have hired as an ISP, he controls those devices. Now, I mentioned that this 192.168 private inside addresses, they're not allowed to be routed on the internet because everyone has many of the different values used. So what happens is your home router, when you want to talk to the outside, to say the web server, netacad.com, what your home router is going to do, he's going to do rocket surgery on that packet, and he's going to change your source IP address to whatever address was issued to you by the internet service provider. So in this case, you're at this workstation here, and you type a request that's going to go to a web server on the internet, maybe it's netacad.com, and when it goes into your internal router at home, he changes that source address to the global address that you were given to by the internet service provider. And then when the answer comes back, he changes that back to your private inside address that you actually used. It can do this many times for lots of different workstations at the same time. This sounds very complicated and sounds like it would take a lot of time, but it does it in the twinkling of an eye, and it really doesn't hardly slow anything down at all. And this adds some security because the people in the outside world don't really know what your IP address really is. So it's hard for them to break into your system. Now, let's look at lastly at IP version 6. So IPv4 addresses were only 32 bits long. There's only about 4 billion possible combinations. IPv6 addresses are 128 bits, 4 times as many bits. Not 4 times as much space, it's exponential. As a matter of fact, there are more IPv6 addresses than there are all the atoms in the known universe. There's enough IPv6 addresses for every single atom in the entire universe that have their own unique IP address. So we get more IP addresses. We don't need to use network address translation. That was a band-aid solution that we had to start using in 1995 because we were running out of IP version 4 addresses. And when IP version 6 was developed, they said, there's a concept, the buzzword is zero config. You should be able to plug stuff together and you shouldn't have to configure it, it should just start working. Kind of like what you can do now. You can plug stuff into your home. If you're on a cable company service, you can just go buy a home router from anybody, plug it into your cable company cable router, cable modem, plug in all your devices, it'll just start working. Auto configuration, so you don't have to configure stuff. So the IP version 6 is increasingly being adopted, and the strategy, the business strategy is in the future, let's change everything over to IP version 6. We're still going to have some IP version 4 for a while, but eventually we're going to get rid of it. And so I think we have one last thing here. So IP version 6 differences, a lot of auto configuration, zero config built in. Instead of the private inside addresses like 192.168, they have something called a linked local address for communications within the same network, like you talking to your friendly neighborhood router. Now here's the last technical thing I'm going to say for today, and then we're going to go into the packet tracer demo. IP version 6 address formatting is written in hexadecimal. Hexadecimal is a shorthand method of expressing binary numbers. And we have our whole 100 bits here in the full form, expanded form. But since it's so long and so hard on the eyes, there are 2 rules to reduce them. One is if there's any leading zeros, here, here, and here, and here, we're going to omit those. And the second rule is if we have several zeros in a clump like this, well, we omitted all the leading zeros and we got this number here, but we still have some zeros in a row. So you're allowed to replace one time only. Take the biggest chunk of leading zeros, a bunch of zeros that are stuck together, and replace it with the double colon. You can't do it more than once, because if you do it more than once, there would be an ambiguity as to how many of them there were. So our original number, which had quite a few digits, is reduced to this much smaller number than compressed form. You can type in either any form you want to, and he will accept it, but it's much easier to type in the shortened form. Okay, hang loose a second. I'm going to stop this, and I'm going to start this. Okay. Share the screen. Share the screen. Okay, so I'm sharing my packet tracer screen. I'm using now a little bit about packet tracer for a year or so now. It's been version 7.3.1, which is the version you've been using when you do your remote labs. There's a new version out now. It looks like the old one. It's version 8, but it's got some nifty new features in it. Now, the way we always did this before was let's take the lab, that chapter 4 lab where you're going to hook up a home router to 2 PCs and then check the IP address information. You would do something like this. You would click on the end devices and you would drag a couple of PCs in the topology, and then you would click on the network connectivity devices and choose a wireless router and put a home router in there. And then you would click on the add the wires method and you would pick something to plug into. And here we have, notice this is logical. How good you can see my mouse moving. This is a logical diagram. It's kind of, it's kind of theoretical. It's not real life. It's not like if you came in the lab and did it, you would see all these different devices up close and personal. And once everybody gets their vaccines, we'll let you guys start touching the wires again, and you can do stuff like that. Well, the old version of Packet Tracer had a sort of a primitive physical environment, but they've got a really fantastic one now. So I'm going to wipe this out. And here is your Gonzo Secret Insider Packet Tracer tip of the day. I'm going to click Physical. And then I'm going to open up our city and open up our building and click on the network closet. And I'm going to put a table in there. You can put racks in there too, but the equipment we're using today, routers and switches going racks. We're just going to use a table. There's our table. Okay, I'm going to expand this once I put the devices on there, and we'll plug them together. Okay, so in this scenario, we're going to do the exact same thing I did before in the logical slide. So I'm going to choose a couple of PCs. And then I'm going to choose, I think I'll have to get another, let me see if I can drop it on top of one of these. A home router will fit on top of your PC. I should be able to do that. Let's see. Let's just try and see what happens here. I'm going to go back and choose home router and see if I can put him on top of this. And he looks like he's violating the laws of gravity, but good. That way it fits in one space. I can blow it up bigger. So I'm going to blow up real big here. Can I get it bigger? Okay. Get it bigger, bigger, more. Okay. There we go. I have to make it a little bit smaller so that we can see the plugs. So we're seeing the real physical view here. Okay. We got 2 PCs, and we're going to plug them together, and we're going to see if they can get an address. Okay, so let's see now. I'm going to go down again. You can see this. Okay, I'm going to click on the red jagged lightning bolt thing, which is pick my wires. Now look at the wires. Oh, I need a copper cable. Okay, so I'm going to click on the copper cable, and I'm going to plug it into, look, there's the Ethernet plug on the front of the diagram. And I'm going to plug that into one of the ports. Look at there, I got a wire. Wow, I can really see what's going on here. Isn't that cool? Now I'm going to do the same thing with the second PC. I'm going to connect the second PC to another plug on the router. Okay, now we've got something here cooking here. We've got these things plugged together just like we would do. If you come and do the lab on Wednesday, this is what's really going to happen, except that the router is going to be physically back on the rack, and it'll be extended to that patch panel cable that you have. It'll be connected. The red and green plugs are 2 VMware workstations instead of 2 physical ones like we have here. Now, in the lab, we're supposed to get these things to connect to each other. So I'm going to click on, let me see, first of all, let's click on PCA, and let's make sure it's called PC-A. So I'm going to dash A. And then I'll go to PCB and make sure he's called PC-E. So let's see. So PCA is here, PCB is here, the wireless router stacked on top. We don't need to configure the wireless router because just like real wireless routers, out of the box, they just start working. So if we flow on the wireless router, he says, oh, we got a couple devices plugged in here, but they're not getting any IP addresses yet. So let's go into our PCs and go to the network control panel and use it's pretty close to what Microsoft Windows actually looks like. Let's go into there and tell them to obtain the IP address automatically, which is a secret code that means send out the DHCP discover message. find that DHCP server that's in this home router here, it's on by default, and have them issue our addresses. So I'll do PCA first. I'm going to go to the desktop, and I'm going to choose the IP configuration screen, which is very similar to what Windows has. I'm going to click the button that says DHCP. And then I'll go to the PCB, and I'll do the same thing. I'll go to the desktop, IP configuration, click the DHCP button. Now it's going to take a moment, but let's check and see now. Let's go to PCA and go to the command prompt. And let me make this a little bigger. Oh, this is kind of hard to read here. Let me go into Packet Tracer and configure the preferences where that makes that type a little bit bigger. I'm doing this on the screen. You can't see it. I'm going to change the font so it's really, really big. Apply it. Oops. Apply. You're going to apply it. There. That's a little bigger and easy to read. There we go. Now, what's that secret command to tell the PC to report to us what its IP address is? ipconfig. And he's telling us it's 192.168.0.100. He's telling us the default gateway, which is the router, is 192.168.0.1. Now let's go to the second PC. Remember, this guy is 0.100. Let's see what the second PC is. Actually, if you float this over here, it'll tell you, but we'll go ahead and go into there to the command prompt. A little bigger. Type ipconfig. He's 192.168.0.101. Here's his value. Well, theoretically now, in the lab, he asks you something like, can the two PCs ping each other? Can they ping the Linksys router or the Cisco router to the top here? Let's try. How about pinging? Well, let's do the 127.0.0.1 first. The loopback address. That should always work. Okay, now I'm going to ping 192.168.0.100. What's the other PC? Now I'm going to ping my home router. Oh, I've got the network connectivity from that. Let's do the same thing on the second PC. So we'll go to the second PC, go to the command prompt, ping 127.0.0.1. That's good. What was my address again? I'm 192.168.0.101, so I'm going to ping my partner, 192.168.0.100. Ping that fine. And now I'm going to ping the default gateway, and that works just fine. So that'll get you started real good on that Chapter 4 lab. The Chapter 3 lab, you can simply use the same configuration exactly, and he just needs one PC. And let's just continue using this PC. And he says, what's the MAC address of this PC? Well, on a real computer, you would type ipconfig/all. And you get an expanded listing here. Let's roll down a little bit. Oh, I got to tap more. Okay. So there's my physical address there. That's the MAC address. And he's going to have you do something in the lab where you go to a certain Wireshark web page and you type in that 00024A part. That's the prefix. And it'll tell you what manufacturer it was assigned to. So this tells us that that's the physical address. That's like your social security number. This is the logical address. This is like the address you're living at or the telephone number that you got. It can change. You can move to another house. You can get a different phone number. You generally cannot change your social security number. You're stuck with that. So that's the super new graphical thing that's built. Let me see if I can drag it someplace else. Will I drag it around here? Ah, he let me drag it there. See, I can drag it around. The wires move. If there's a bunch of wires in there, you can float your mouse over one and it'll turn that wire. You can see exactly what color it is. Float the wire over this one. They'll do whichever color that one is. Now, you can do a little bit of this physical stuff on your existing version of Packet Tracer 7.3.1, but it doesn't show the nifty wires. It shows the wires all tucked away real well. But it'll work pretty much the same way. Except when you right-click on it, you'll get this. Oh, remember our logical diagram? Let's go back to our logical diagram. Okay, this is the way it would look like if you did it in the old style version. And how would I pick, how would I pick a different connection here? I'd right-click on there and be able to choose a different port. Let me go to here. So yeah, I use ports 1 and 4, ports 2 and 3 left over. I could add another PC and connect it to port 2 or 3 to that. But I like this. This is a theoretical, logical diagram, and I really like the physical lat one because it makes more sense. So that's the super feature. I wanted to show you that present there for that. And let's see now, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, I've covered pretty much everything I want to cover. Wednesday will be our either remote or in-person lab. If you come in person, you get hooked to a real wireless router, home router, and use that in your virtual VMware PCA PCBs. And if you do it virtually, you can do it like I've illustrated here using the packet tracer program. Either version will work just fine, whether you use logical or physical, but the new physical is really keen, isn't it? Okay, hang loose. I'm going to go on mute. Oh, wait a minute. Let me stop the recording first. I have to be down here to do this.